So our topic today is we are going back to basics. So there's a couple, as I've been doing this and thinking about it, I realize that there may need to be multiple episodes of this, so to say. Because back to basics in this format, we are going to be talking about drivability concerns, right? So our basics for fuel and air and spark and compression, right? We sometimes, and I'm pretty sure we've all done it, sometimes you just go and get into that mode where you're trying to diagnose something and you totally forget the fuel, or you totally forget about the spark, or just you run around in circles for a while and you end up remembering a little bit later and then you finally do it, right? Same thing as like electrical. Like I said, there could be multiple episodes of this, but if we were talking electrical, like the time you don't check the fuse, you check all the wiring and check all this other stuff, and you forget to check the fuse, right? It's these basic things that we all seem to forget. We just get in our head and just do whatever we're doing diagnosing. But sometimes we just forget, hey, it needs fuel, hey, it needs spark, right? So let's talk a little bit about the basics when it comes to drivability. And then also we're going to go through some tests that we can do to help us with these in the drivability scenario. So I'm a big believer in having a good workflow, a good repeatable workflow that you can just go through and check the boxes pretty much and make sure you're not missing anything. That is one good way to not forget some of the basics. Things like intake the customer, capture their customer complaint, do a road test to verify that complaint. Then when you bring it back into the shop, inspect it. Might uncover the cause of the complaint or maybe some other issues that might show up as well. A little vehicle inspection. Then, of course, we want to do a pre-scan on every vehicle, check all the modules for codes and see if there are any codes in there that might give us a direction. Then we're going to perform the actual diagnosis to determine the cause of the problem and then hopefully repair the problem. And then once the repair is done, we may need some sort of a reset, relearn, calibration that might need to be done. So we would do that then. Then, of course, we would take it on a road test and then post-scan it at the end to verify the operation and verify there are no codes left, right? So that is a good standardized workflow that really anybody could use. Really starts though with intaking the customer, right? So we need to define the problem. So what kind of a problem is it? Is it a drivability problem? Is it a no start? Is it a noise? Is it a drivetrain problem? Is it an electrical problem? Use a customer interview worksheet if you can. That way you have standardized questions that you would ask, or you can even have the customer fill it out and say, hey, here's what my complaint is. That way you don't have that lost in translation between what the customer says to the service writer, if you have one, to the technician, right? So you want to close that loop and have as little confusion as possible. So if you have Shopkey or Mitchell, they actually have these in there as well. You can find them in the general section in the service manual. I might be able to show you that a little later. And if it's a drivability problem, for sure, you want to do a road test and a pre-scan to go through and see, are there any codes, right? You want to make sure that that's the, where are the codes and what are the codes and what could be causing the problem. The diagnostic strategy, of course, is going to be depending on the problem. If it's a drivability problem and no codes, check TSBs, see if there's anything for the symptom you're getting, or check experience-based information, something like our SureTrack. And then remember, like I said, the basics of combustion: fuel, air, spark, and compression. Check your fuel trims, check your fuel pump, check your injectors, check ignition, check the mechanical issues that might be in the engine. And we're going to step through all of those different things, starting with TSBs. So TSBs, of course, you want to check them first as early on as you can. Once you have some sort of a direction, like if you have a code to start with, or if you have a symptom, like for this example, I put in engine runs rough, right? So if we go to running rough, we can go in there and looky there. There's some TSBs available for that. If I go in, there's two under engine control system category, and one of them is engine misfire due to a failed ignition coil. Okay? So that deals with our spark part, right? And this is an interesting correction here. So the current ISTA misfire test plan, so ISTA is their factory tool. The test plan for these engines can be lengthy to complete and does not provide an effective method to diagnose a faulty secondary ignition component. If basic diagnosis determine the cause to be a faulty coil, follow the inspection and replacement procedures listed below. Make certain to test drive the vehicle after repair is complete to verify the effectiveness of the repair. Only if misfire faults or rough running are still present, continue with further diagnosis as recommended in the test plan. So basically what this says, if you scroll down a little more, is they've put Bosch coils in there, And I guess they had a pretty high failure rate on those Bosch coils. So the fix is to replace them with the Delphi coils there. So that's a fairly easy fix. But hey, if I was working on one of these and they had some sort of drivability problem, and I pulled out the coil and it was the Bosch coil, then I would know that we need to replace them with the Delphi coils. That is the fix from BMW. If you find any Bosch coils, replace them all with these Delphi coils. And that's the fix. Then if there's any other problems, you go on with that. But this is that's pretty cut and dry, and it's fairly quick, right? I read a TSB. Oh, I could probably pop one of those out. Oh yeah, it's all black. It's a Bosch one. Replace it with a Delphi one. Or how about experience information? What have other technicians done in this particular case? So in Shopkey, and also if you have a current scan tool, you're able to access these on the web as well as a scan tool. But if you have a current Snap-on scan tool linked to your Snap-on account, which you should anyways, because then the Snap-on Cloud will work and security link will work and all that. But as long as you have a current tool linked to your account, you can use that same username and password you use to get in your Snap-on Tech account to get in here, and you can get the SureTrack information in there too. So real fixes, that'll be available on the tool and also on the web. So we have this here ranked by how many times it was a confirmed fix. Then we have top repairs, which is our graph, which you may have seen on the scan tool. If you've used the Snap-on scan tool before, you may have seen this up at the top of the screen, and that gives you a ranked, here's what got done to fix this problem, and it's by mileage as well. So it's got miles down there up to 200,000. Then we have causes and fixes, which takes that data and it splits it out based on possibly even not a code, but in this case symptoms. Could even be multiple codes and symptoms combined, gets us to where we need to go. So if we have simply engine runs rough, then it looks like it's could be any of those things, and it ranks them over here. But what if it's runs rough when accelerating? Then most likely it's a coil and spark plug and an ignition coil. So either or. So you see how it kind of breaks it down, narrows it down. That helps you get to that silver bullet, that magic wand that everybody's looking for to fix a car, right? What fixed this car? Multiple times. So 185 times the ignition coil showed up, and that fixed the car. All right, so that's our information side of things, right? TSBs, experience-based information. What have other techs done? Now, what can you do when you go in, and what things should you check or could you check in order to help you with drivability? So fuel trims first. So fuel trim is a window that allows you to see what the computer's doing to control fuel delivery and determine how the PCM's adaptive strategy is operating. And this is, I think, still somewhat of a mystery to some folks, like wrapping your head around positive and negative fuel trims and things like that. So basically what happens is when we're driving down the road in closed loop, right, where it's a closed loop, the computer is always trying to get the mixture to that 14.7:1 air-fuel ratio. So the oxygen sensor is going to be in charge of this. So the front oxygen sensor sees, oh, we're lean. With too much air, not enough fuel. So it's going to say, hey, I need a positive fuel trim. We need to add fuel to this mixture in order to make it not lean. And then it'll add fuel and it'll add fuel and it'll add fuel. And eventually it's going to get to a point where it say, oh, whoa, 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 now we got too much fuel. Now we're rich. So when it's rich, it calls for a negative fuel trim. Pull some of that fuel away. Make it less rich. And then it pulls the fuel trim away. And then it goes and reads lean, and then it adds fuel, and then it reads rich, and then so you'll constantly see the oxygen sensor, if you're watching a zirconia oxygen sensor, just goes back and forth all the time, just going rich, lean, rich, lean, rich, lean as it's adjusting the fuel. Now, of course, newer vehicles can adjust them almost microscopically at this point, and they do operate over a wider range of air-fuel ratios now as well. So you get those wideband air-fuel ratio sensors are a little bit different, but the fuel trim still works in the same fashion. If it's lean, we add fuel. If it's rich, we take fuel away. So the relationship for fuel trims when it comes to short-term and long-term, so the oxygen sensor, as I just said, is going to feed into the short-term fuel trim. Adds, subtracts. Over time, if this short-term fuel trim is going too far in one direction, like continually adding, and it gets up to maybe 5, 6, 7, 8, 9, 10%, then the short-term fuel trim is going to feed in a long-term fuel trim, and the long-term fuel trim is going to see, oh, we're positive So I'm just going to go with a straight positive, up 2% or something like that. And then the short-term fuel trim adjusts to that. And then you can just kind of see how it goes. If it's going way in one direction, especially your long-term fuel trim, that indicates that there has been a problem with the car for a while. If it's only on the short-term fuel trim and not affecting the long-term fuel trim, it hasn't been going on as long. So let's see how this kind of works. So we're going to create a vacuum leak on a vehicle, read the data, observe the oxygen sensors and their relationship in comparison to the fuel trims, and then we're going to repair that vacuum leak and then see what happens. So it's just a little science experiment using data on a scan tool. So rear oxygen sensor here, air fuel ratio sensor here. This vehicle has a zirconia oxygen sensor in the rear. Also, this is a Subaru. So on Subaru, some of them, in the OEM data anyways, call it air fuel correction for short-term fuel trim and air fuel learning for long-term fuel trim. So it kind of makes sense. I don't know why they didn't use the industry standard. Well, of course, there's a lot of things they do that are an industry standard, but it kind of makes sense if you think about it. We're correcting on the fly, so air fuel correction is short-term. And then learning would be, hey, I'm learning what's going on long-term. The short-term correction is teaching me. So that's what we have on the screen. So rear oxygen sensor reading rich up on the top, or yeah, it usually goes more towards the rich side of things when things are operating normally. Air fuel ratio sensor, we want to keep it at a 1, would be 14.7 to 1. Stoichiometric. So we see right here, it's roughly 1, give or take. 1.01 is this little bump right there. So you can see we're right around 1.99, somewhere in there, just idling along normally. Then I start cracking the hose. I just took the brake booster hose and just kind of slowly cracked it off the intake manifold. And then it goes up. And then I opened it a little bit more, and then you can see how it reacts going up. And then when we finally open it pretty wide, it goes full lean. Everybody goes full lean. So let me just get this going over. So there's where we start moving. And then it comes up and then it goes full lean. So air fuel correction, short-term fuel trim goes up to plus 35%. Long-term fuel trim is going up. It gets up to a 6 in this area. And then even after we correct the problem, everybody goes down to full rich at that point. So full rich on a zirconia is way up the top. Full rich on an AF sensor is all the way bottom. And then due to that, our short-term fuel trim goes negative, but you can see our long-term fuel trim was still going positive because it lags that much. We had plus 35% for a while. So it says, oh, well, I guess I got to adjust again because we're plus 35%. But over that time, things have adjusted, but you can kind of see that offset between the short-term reacting quickly and the long-term not reacting quite as quickly. And then over time, it slowly adjusts and goes back to where it was once the repair is complete. So that'd be a PO 171, a lean condition, right? And then we'd be able to see, oh yeah, our air fuel correction is way high on the positive side. And you can use them as a rule of thumb, right? Long-term and short-term fuel trims also, I'd say kind of more on the long-term because this is what we're trying to see. Is this a problem or has it been a problem for a while? But you can use these percentages with the short-term fuel trim too and see how kind of the severity of the issue at this time. So plus or minus 5%, everything's doing what it's supposed to do. So you don't really need to worry about that. Yellow light, you got to kind of get a little worried when it gets in the plus or minus 6 to like plus or minus 19%. I say double digits, you should be worried about something going on. Possible wear and tear or maintenance issue, clean, inspect, and service. And then red light, anything over plus or minus 20%, either direction. That means the PCM recognizes the fuel trim is reaching a set threshold and a possible 1.5% rise in emission standard, which is what the standard is to set a code. So that's going to set a code and it's going to put on the check engine light at that point. Either too rich or too lean. You'll probably get a 171 or a 174 code. All right, so that's our fuel trims. Now we're going to talk about some components like the fuel system. So when I'm testing components, what I want to do is I can test them in one of these 3 ways, really, if you think about it. Electrically, mechanically, or hydraulically. So I can do it electrically, but to verify the circuit integrity and verify the components actually operating and making sure the circuit's doing what it's supposed to do. Mechanically, I can view current flow and see the current flowing through the circuit through the component, and I can verify mechanical motion. I'll show you a couple tips on that. And then hydraulically, view a pressure change or drop, especially if it's a fuel system, and verify the state of flow. So those are the three real ways we test a component. First thing we'll talk about is where the fuel comes from is the fuel pump, of course, right? So a conventional brushed fuel pump is going to look something kind of like this. So this is just a typical brushed motor, but it's going to have brushes. It's going to have these commutator segments, and it's going to have the rotor coils. So the coils rotate, and then the stator stays stationary. So the magnets are stationary, and the rotor rotates, right? Kind of stator stays still, rotor rotates. So you can that's a good mnemonic device to remember that. But brushes provide the voltage to the coils, and then the coil spin becomes an electromagnet, and the magnets are stationary. So fuel pump kind of like this. So you get your strainer, goes up through, you got an armature in here, and that's where all the windings are. And then you have your brushes here that contact those commutator segments. Also an anti-drain back valve to make sure that it doesn't drain the fuel all the way out of the line so you can actually start the vehicle. Pressure relief valve there as well. So if you have a snap-on scan tool with guided component tests in there, which would be anything with a scope, so Tritons and Moduses and Zeus and Varus, any of those tools, Vantage, any of those that have the guided component test function will have a fuel pump current ramp test in there available for you. So this is the easiest way to set it up. If over time, when you learn what the settings need to be, you can just do it in the scope if you really want to, but it's pretty fast to do it this way. So you're going to take a little amp probe and you're going to place the jaws around a wire anywhere in the fuel pump circuit. If you can get close to the pump, put it there. Otherwise, a jumper for the fuse, if it's got one fuse for the fuel pump, pull it out, put a jumper in, put it around that. Or the same thing with the fuel pump relay, pull it out, put a jumper in, and we can watch the current flowing through the circuit, and you're going to be looking at the current flowing through the commutator. Now, most automotive fuel pumps that are brushed have 8 commutator segments in the motor. And there's an example of a badly worn one over there. Each of those bumps you're going to see on the scope screen are going to represent one of those commutators going by in the motor. So we can see they're kind of going up and down and up and down and up. And that's as it spins by, the current goes up and then the current decreases as they go past. So if you want to make sure the bumps are rounded and there aren't any fairly rounded, there aren't any missing. If you look at a brand spanking new one, it's going to look like a shark fin. It's going to be very pointy because nothing's worn in yet. So it's just going to be just very, very sharp points. And it'll slowly over time, it'll just kind of wear down, I guess you could say. So if we count out 8 bumps, though, that's 1 revolution of the motor because we know this one has 8 commutator segments. So number 1, 2, 3, 4, 5, 6, 7, 8, and then number 1 again. So that contains 1 entire revolution of the motor. You can calculate the rough RPM by counting how many times it revolves in a 10 millisecond window. So 1 revolution in 10 milliseconds equals 60,000 RPM. In this case, it turns about 1.5 times. So we get 8 and then 1, 2, 3, 4 again. So that's about 1.5 times. Pump's turning about 9,000 RPM due to that math. Now, you want to know what the actual rotational speed of the pump is because that dictates the volume of the fuel. Pressure is controlled by the pressure regulator. Volume is controlled by how fast the fuel pump's turning. On a newer vehicle, the brushless fuel pump and a high-pressure fuel pump, it's a little bit different, but it's still the supply, right? The volume is important. So we can do some simple math using the cursors from the previous slide. So if we take and look at the measurement, how long does that take to do 1 rotation? We get 6.95 milliseconds. So 1 revolution takes 6.95. There's 60,000 milliseconds in a minute. So if we take that 60,000 and divide it by how long it takes to turn 1 time, we get our revolutions per minute. In this case, 8,633 RPM. That is a good fuel pump, cranking right along. You want to see about 6,000 RPM or greater. On a worn-out fuel pump, when you get down to about the 3,000 RPM or less, you're going to have a drivability problem because it can't supply that fuel fast enough in enough volume to the front of the vehicle because it's not turning fast enough. So it's set to rotate at that speed to push that amount of fuel up front. Now, when it comes to a brushless fuel pumps are made and operate kind of in the opposite way. So on the brushed fuel pump, the magnets were stationary on the stator. On these, the windings and the coils are stationary on the stator, and then the rotor contains the magnets. So we have 3 circuits in here with positive and negative, where we can turn these positive and negative. So as it turns, you can see these are permanent magnets. So red is south and blue is north. So as it goes by, blue will repel blue, red will repel red, blue will repel blue, and that's just kind of how it goes along, right? So red is repelling red right now, blue is repelling blue, red is repelling red, and it just kind of moves around to push it around by using that repelling. The controller provides a voltage to the coils. The coils are stationary and the magnets spin, like I said. So this is out of a Camry. So a fuel pump control unit is back there, and we have our U, V, and W legs that go over there, and then we have fuel pump ground as well. So UV, W, and ground, and we can take a look at that and see what's going on inside the fuel pump by using both electrically and using a low amps probe. So these are our 3 circuits right here. And I have a low amp probe on this circuit right here. So we can see how it reacts. So in this case, it also flips. The polarity flips because we have to have a positive and a negative. So we have to have a north and a south polarity as it pushes around. So we can see this one kind of goes down and ends on a down note. This one ends on an up note, and then this one would end on a down note again. So it goes up and down. And then we also can see that with the current flow as well. So in this case, we have positive current, then it shuts off that magnet, no current at all. We're at 0 amps, no current, and then it turns on in the negative this time, and then it turns off, and it turns on the positive, and so on and so forth. So you can check the condition of how that's working. It's kind of just like a pulse width signal, and it just turns it on, turns it on, turns it on, and you can see one goes up, one goes down, one goes up. So they alternate, and they're 120 degrees apart because of the circle on the 360 divided by 3 is 120 because we have 3 legs 120 degrees apart. You can also measure the time that it takes to turn using the same technique as we saw before, except you have to go here and then over the next time because you have to go through 2 times because we got 1 positive, 1 negative, and then see how long that takes. So this is actually in a little tight. I probably should have zoomed it out a little more, but you can see at least 1 time through of the magnets. High pressure fuel pump, you're really not going to check it much electrically because this is a mechanically operated pump. There's a little rounded square, it kind of looks like in this case, on the end of a camshaft, and then that pushes up on this pump, which increases the amount of flow going through there. So we have accumulator, spacers, we have this overflow valve, we have the plunger that pushes up on a diaphragm, and it increases the amount of pressure in the fuel because it compresses it down into a smaller space. So that's kind of how that works. It's very mechanical. There might be one like pressure sensor on there possibly, or this is a spill valve, I guess, that it can use to kind of regulate the pressure a little bit. But by and large, it is a mechanical device, and failure point's usually on the camshaft. So. Now that we got the fuel in, we can look at the fuel injector. Now this is going to be a conventional fuel injector, not a direct injector. I have other classes where we go through all the different types of injectors and stuff like that if you want to check that out. But for this purpose of this class, we're just going to talk about a standard fuel injector. So this line is pressure, the yellow line is electrical, and the green line is mechanical. That would be your current probe. So we got a current probe, we got a back probe, and we have a pressure transducer. So if we look at voltage, like I said, standard injector, so it's going to be provided power from the battery, and it'll be grounded by the ECM. So when the ECM decides to ground it, activates the coils in there, opens it up, starts spraying fuel, and we're going to see it go down. Once it is open for however long the computer tells it needs to be, it'll snap shut, and then all that voltage that was stored in these coils gets kicked back in the circuit. So we get like over 80 volts on that one. Then it comes down, and this is the point where the pintle actually snaps shut because we have a little bit of time in the motion. That's the point where it actually snaps shut, and you can see another little bump there, and then it goes off. Amperage is going to do kind of the same thing, but in reverse. So amperage is going to increase. You want to see a nice smooth ramp go up. In this case, we have a little bump right there. That little bump is the point where that pintle actually leaves the seat and starts spraying fuel, because there'll be a little bit less resistance at that point. So we'll have a little bit lower amperage that needs to be to overcome that resistance in that case. Now you want to keep an eye on that. If you're watching a single injector and you're testing it, you want to make sure it's opening at roughly the same point every time, as long as, you know, the RPM's the same. We want to make sure it's opening at roughly the same point every time. If it's there, being really erratic, you might have a broken spring in there. It's just not opening and closing at the same rate every time. So most likely a mechanical issue inside the injector. If it's moving up and down this ramp, it opens the same place every time, then we know it should be mechanically sound. And it's going to go up, and then when the injector closes, it comes back down to nothing. On this vehicle, the pressure transducer didn't really, it wasn't a huge drop, but you'll be able to see the spike at the end, which is interesting. So you got a pretty steady 35 PSI right there, give or take. And then when it opens, it kind of goes down a little bit. In this case, we're not seeing a ton of movement going down. But certainly when it closes, we see a spike. Now, why would that be? Because it's spraying. All of a sudden, the door closes, and I still have fuel behind me coming in. So then it gets kicked back out because it has nowhere else to go. So we get a little bit of a spike, but then it recovers again very nicely back to that 35 PSI. So that's 3 ways of testing a fuel injector, standard fuel injector. Let's go to the other part of our story, one of our other parts of our story, ignition. So ignition is a couple different tests we can do. In this case, this is a cranking test on a known good engine. You want to make sure you'll know that they're fairly even. They should be fairly even. That indicates a good running engine. Otherwise, we have a cranking test on a vehicle that was in the middle of getting its spark plugs changed. So we can see these 3 are fairly level. This one's way off the charts. Want to know why? That spark plug was worn out. So a large gap on a spark plug is going to have a larger firing line going on with it in order for it to cross that gap. So there you go. You can also look at the spark line. So after the firing line happens, we can take a look at the spark line. It should be fairly level, and we should see a little bit of turbulence in there. The turbulence is actually the little minuscule molecular changes in how rich or lean it is in that one particular spot. So we'll see that turbulence. And then in this case, we get a little extra little wiggle right there. Depends on how efficient your coil is, whether or not you get that. Then I decided to lean this one out too, pinched off the fuel line going to it. So we can see that it went nice and level. And then boom, went off to the races lean. So when it is lean, your spark line will go higher. And then if it's rich, spark line will go lower. So in this case, it went down before it leveled off, right? So it goes either way. Lean is up, rich is down. By checking the spark in the ignition system that way, you can really see what's going on inside the engine and what the problem might be. Next ones are compression, right? So we have a couple different ways we can check compression. One of them is relative compression. So that'd be relative to each other. As you're cranking over the engine, how are these cylinders matched? So in this case, this is a known good vehicle, and we can see it's pretty much the same. What we're doing is we're checking the cable to the starter and checking how much current the starter is drawing from the battery in order to see how the engine is running. If the compression's even, it should be cranking over evenly, right? If it have low compression, then it's going to be cranking faster on that one cylinder, and you'd be able to actually see that. And that's why we have these 2 green lines, which are the injectors. Right, so the injector number 1 and injector number 1 again. So that's 1, 2, 3, 4, 5, 6. So it's a 6-cylinder. Right? And then it fires again right there. So that's relative compression on a good car. Here's one on a broken car. This is a Jeep, and it had a clogged catalytic converter on the odd bank. So we had low compression on those banks because we couldn't get anything in. They weren't able to get anything out, actually. No, so the pressure was high. Never mind. Pressure was high on that side. Large pressure pulse, 135, and a low vacuum pulse. So you can see that there's bad stuff going on right there. So this was a relative compression test. Like I said, it was clogged on one side. Running compression can be done in cylinder while it's running. Here's an example of one that is good. So the compression comes up, and then the piston starts going down after the we're on the expansion stroke here, on the power stroke. Then you should see a vacuum pocket. Then you're going to see your exhaust. Then you're going to see the intake valves open, and then you'll see a vacuum again. and then you'll see compression, and then you'll see it drop back down there. Now, running compression, the actual compression values are going to be much lower when it's actually running than versus a static compression test, just so you know. Here's an example of one that wasn't running very well at all. That's one cylinder, and you can see not much going on with pressure over there. It's pretty much just a dead hole at that point, just pumping air around. And then here's a companion cylinder to that one we just looked at, right? So there's the bad one, and then there's the one next to it, and we can see that we have a good pulse up there and good vacuum down there. And we can see that the exhaust doesn't go above 0, which we don't want to see, because if the exhaust goes above 0, that means we have a clogged exhaust. And this is the one with the bad cat that I was talking about earlier. They did a running compression test on it, and the exhaust went up high, and it went above 0, and it kept going up. So that indicates that that exhaust pressure was not getting out, and then you can't pull in nearly enough on the other side. Due to that, there's already pressure in the cylinder, so we can't get more air, a lot more air in there. So we get a very small vacuum pocket, and then in that case, very small compression on the other end, because we don't have a lot going on. And then I just wanted to check everything at the same time on my vehicle when I did this. You're supposed to leave the injector off when you do it so you don't wash down the cylinder, but I just wanted to see kind of, how's my engine running? What's it look like when it's running? What's the engine look like when it's running? So here we go, compression comes up. This is the coil. So at that point right there, the current ramp on a coil. So the coil fires, a little bit before top dead center. Then top dead center happens, and then we have our little explosion. And then down comes the piston. We get a vacuum pocket. And we have exhaust. This is a 4-cylinder vehicle. I see the other cylinders, actually. You can kind of see some crossplay going on. And then we have where the injector would spray, and then the intake valves open like right as soon as the injector sprays. So you can see how it changed, the pattern changed. Get a little bit of swirl going on in there. And of course, there's valve overlap. And then it comes down, and then we have our vacuum pocket, and then it compresses again, and so on and so forth. And as the engine runs, that's how it runs. So there you go. That's my slides. Let's look at a couple little things that you got in the tool that we can work on, that we can see. So here is our scan tool. First thing I want to show you, actually, that I didn't show the first time I did this, is, let me just pull up a vehicle so it's faster. Well, I actually don't think I have it loaded in here, so I guess I'll just do it that way. We're going to do 2012 BMW 228i. Doesn't matter, but we have to load a vehicle in order to access this, so. Okay, so if you have ShopKeeper Mitchell, you can access the service manual. And then in the service manual, it is going to be under general information. And then let's see. We have a bunch of different things. Let's go with basic troubleshooting. Engine performance troubleshooting. That does not have the, it doesn't have the map. That's just what you can do. Where is it? It is in, I'm going to quick lookups quick. Specs. No, that's different. I always lose it here. Let's see. Engine performance. Testing and diagnosis. You're in operation? No. Man, I should have looked this up earlier, huh? Guess it is under general information. Engine performance. There we go. Map engine performance. So this is a maintenance check sheet that you can go through. All right, check that off. Also should be above that. Overview of requirements. And then we have a bunch of other stuff that tells you how it works down here. So there's a lot of these different things in here that you can take a look at. Diagnostic routine outline, mission standards. Hey, even it goes through a fuel injector waveform tutorial. Look at that. So lots of different things in there. And more. All right, so let's I'll go into guided component test here, and I want to show you a couple other things that are in there. So there's classes built in. And if I go into how to, we have things like the 15-minute pressure transducer diagnostics class. And that'll talk about running compression tests, actually. So you can go in there and for more details, see the 10-minute running compression waveforms class. But it kind of walks you through how to do the test and how to hook things up. What else is in here? We're going to go into the car itself. Pull up that 328i. 52kp. And if we go into engine, we can see things like the, well, we actually have a compression test that we can do. A lot of vehicles have this listed. Relative cranking compression with using a secondary ignition probe. So what this does is you put it across the battery terminals, and then you can measure the voltage drop as the starter is turning. Instead of looking at the current flow, you can look at the voltage drop across that. So the regular, actually it's the regular test leads and a special ignition preset. So you actually go in there and hit view meter. It's going to be set up on an ignition probe, but you're going to be using the voltage probe, and then you would be able to see it going up and down, kind of back and forth like that as it's cranking. So helpful little test that you can do. We developed that test. Also in here, we could do fuel system. So we could look at the fuel injector, right? Signature test, shows you what it's supposed to look like, shows you where to hook it up. Automatically sets up the voltage and time for you. If we go into fuel pump, you can do a current ramp test on the fuel pump, and that talks about everything I just talked about on the fuel pump earlier, looking at the commutators, hooking up with a at the fuse box. You even have the RPM calculation right there. All right, so 60,000 milliseconds in a minute, divide. All of that's in there. Shows you how to hook it up, where to hook it up. And then also we have some ignition tests in here. So primary tests, we can do like a signature test on the primary side. It's going to show you the coil. It's going to show you here's a single spark ignition, here's multi-spark ignition, which this one actually has. And then secondary tests as well. And we can check burn time on the secondary ignition with a special adapter that we can use, and we can look at the burn time, and we can look at the signal there. All right, so that is, I think there's one more thing I wanted to show. Let's see. Oh yeah, I can go into the regular ignition scope as well. So if you have a Zeus or Zeus Plus or a Verus Edge, you go into the scope, it actually has a full ignition scope function. So you can do like parade patterns, cylinder patterns, raster patterns. I don't have an example to show you on the screen because I don't have it connected, but you can actually hook up your ignition probe and see all the ignition, all the cylinders all on one screen and see differences in that. I talk about that in some of my other ignition testing videos, so we don't go too deep into it here because we're already going a little longer than normal. So yeah, a lot of different things you can do in there as well. So that is back to basics, drivability. I think I need to like subtitle it or something, right? Or do parentheses. So let's talk. That is our topic for tonight. So let's talk about what we're going to talk about next week. So next week, we'll be returning to our OEM specific ADAS training and Honda that week. So we're going to talk about what is unique when it comes to ADAS with Hondas. They do have a couple interesting quirks to say. So join me again. Same time, same place, every Tuesday. If you want to join me on Zoom, go to snapon.com/OT. Otherwise, you can join me on YouTube by scanning that QR code right there. That'll bring you to the YouTube channel and automatically subscribe you. 6 and 9 Eastern every Tuesday. And we just talk about it. YouTube is on the 6 o'clock Eastern. And our Facebook page is on the 9 p.m. Eastern class. Also, if you want to see any of the other classes in this series, we actually have 114 classes. I got to update this slide, but it's anywhere from intro to ADAS through our OEM-specific ADAS training. We have component testing in here, VVTs, HVAC, diesel emissions. Went through a whole component testing series. So there's a lot of good information in here, and it's all about half an hour long, 45 minutes long, depending on questions and things like that. So if you want to see that, once again, go to the YouTube channel, youtube.com/Snap-on Diagnostics. Also, do we have your email address? If we do not have your email address, you're missing out on some good diagnostic information like technical focus articles, SureTrack blogs, quick tips, new product releases. Hey, we just released a new product a couple weeks ago. It's called the Triton. It's really cool. You Should look into it. But here's an example of one of those technical focus articles on timing chains. Here's another one on the SureTrack blog talking about that. So if you're not getting these emails, scan that QR code, enter the information, and you'll start getting them. It is free. All right, let's get to questions. But before we do, one more thing. I got to make sure I mention my buddy Keith, who also does free diagnostics training. His is scan tool specific. So on Wednesday, is it on Zeus and Zeus Plus, and Thursday it's on Training and Apollo tools. Takes you everything from soup to nuts. Let's turn it on. Let's set up your Wi-Fi. Let's talk about security link. Talk about all sorts of different things. And he will go through that with you. About an hour and a half, hour and 45 minutes with a 5-minute break in between. Talks about everything about scanner, everything about scope. So definitely worth your time if you have one of these tools. You want to learn a little bit more. All right, back to questions. If you're on Zoom and you joined a little bit late, just look for the Q&A section up there and ask your question. I do want to say hello to the folks over in McLean, Virginia at the VFW with my buddy Ephraim. Learning some stuff tonight. Hopefully he'll take good care of you after I let you go. If you do have any questions, you guys can also type in for that too. Jay McCall says, thanks for the class on the Zoom. On YouTube, we've been a little active today. So JLE Lobo says hello. Nick says hello from the UK. Get to sleep, Nick. I know you're here every Wednesday and it's late, but DK says hello. Nick says thanks for the free training. Let's see. DK says I have Apollo D9. I really want to upgrade my scanner so I can have access to the scope and other additional tools. Hey, as you can see, there are quite a few different things that can be done with the guided component test and the scope. So he said he fried an injector with a power probe. He loves that tool, but doesn't care if you push the wrong button. Yeah, that's for sure. Garage Day says hello as well. And then Nick says, can't wait for next week. And JLE Lobo says, always good information when you go back to the basics. So thank you for that. And with that, I got another one on the Zoom. Ephraim says, no questions there in Virginia. So thank you very much, guys, for your attention. And with that, that clears the big board. So thank you very much for spending a little bit of time with me. Hopefully you learned a little bit more or remembered a little bit more about your basics that we all seem to forget at some point. So hopefully you can take some of these things and use it in the shop tomorrow. With that, I'd like you to enjoy the rest of your week. Enjoy your weekend. Have a nice night and take care.